Hi friends, welcome back. I'm Terry Burns and this is a continuation of my class on the Monas Hieroglyphica or Hieroglyphic Monad of Dr. John Dee. You are up to Theorem 20 now if you've been following along with me. In fact, we are up to the second installment of Theorem 20. And what we're going to look at here is Dee's attempt to solve the ancient Greek problem of the doubling of the cube, or the so-called Delian problem. But it's going to get mixed in a bit with some realpolitik here. And as you'll see, by the time that we finish this theorem, he actually is giving you two different solutions, and you can decide for yourself if they solve the Delian problem. Those of you just joining us, I'm assuming that you know who John Dee is. I'm assuming that you know what the Monas Hieroglyphica is, but this is a rather advanced video. I'm also assuming that you have read and understand the letter to Maximilian and the first 19 theorems, and you are picking up the references to supporting texts like Plato's Timaeus or the Sefer Yetzirah, because Dee is treating this glyph, his monad symbol of everything, also as a mnemonic device for some key points in those texts. If you need to get up to speed, I have 4 different playlists below. I'd love to have you join me in this class. But for those of you who have been hanging out with me here for the last couple of months, let's get started here. We've gone through some pretty difficult theorems in 15 to 18, and they have been between what we might call an emerald tablet sandwich. That is 2 very short and easy to understand theorems that are essentially restatements of the emerald tablet of the thrice great Hermes, or Hermes Trismegistus. And this is, of course, a Hermetic work, so it's no accident that that is happening. John Dee calls the little monad glyph itself his London symbol of Hermes. So we're at 20, and just a quick recap of how we got here and what those difficult theorems were that we have gone through, because they're also just bizarrely wonderful. There was 15, nature rejoices in nature. That's the one that my friend Vincent Bridges used to call the tantric key to the whole thing. And we saw how that quote in ancient Greek seems at first to be referring to Democritus, then maybe to the Turba Philosophorum, except oops, that's in Latin, not Greek, and then to the Codex Marcianus Graecus 299, especially the letter Isis the prophetess to her son Horus. I've got a whole video on that below. And not that letter so much, but Dee's time collecting manuscripts and copying the Codex will be significant here in 20. We also looked at, in Theorem 16, that's his LVX, Latin for light, as the light of the cross, the crux of the matter. But that's also one of the big places where he introduces us to conic sections, which are key to this theorem. That's also the only known place of the signs of the adept used in modern esoterica. When we get to 250, Theorem 17, that's 252 has the philosopher's stone. He never tells us why, but upon studying it, we realize that it's the idea of the multiplied powers of the 3 different kinds of letters of the Hebrew alphabet as the creation of everything, per the Sefer Yetzirah. By the time you get to 18, you have 2 riddles that seem to be about alchemy, and they kind of are if you mean spiritual, not physical alchemy, with the egg. Oh, and if you mean Kabbalistic spiritual alchemy, which Dee does, in the egg when you solve it by going up the tree of life in kind of reverse lightning flash order. When you get to the one on the spiral, you are becoming like the light of the cross, or the Christos, or Jesus associated with Tifereth, and the light of the scarab is just, as we talked about, a reference to Jesus or the Christos, and you're anointing yourself, Christos being the anointed one, and hopefully maybe purifying the eagle, that is the rather warlike Holy Roman Empire, which will also become relevant in this theorem. Then there's another statement of the emerald tablet. In the second one, we can explicitly connect that sun and moon creating the one thing to the middle pillar, and we're at 20. Okay, so buckle up and we will jump into 20. Last time, I suggested that this opening clause where Dee says we have sufficiently demonstrated above, that he's referring back to his discussion of the rectilinear cross and that center point that he displaces from it back in Theorem 6 and 7. And then this is just the first part of it, but as we get near the end of the second paragraph, we get these words that I've put in bold. And in fact, I'm just going to read them to you on the next slide here. So this is where D says, I beseech you, my God, to forgive me if I have now sinned against your majesty by revealing such a divine mystery in published writings. Now, I know when I read this the first time, and I hadn't translated it, I was reading it in the Jostin translation. I was like, what? In other words, he's gotten real excited. It seems like he's discovered something amazing. But what it is kind of hard to figure out. It's like in that Isis the prophetess letter when she gets this secret of alchemy from Omniel and teaches it to Horus. But then when you actually see the words, they fall really flat. It's like, what? So maybe it's not the words. Anyway, your homework was to try to figure out what John Dee had thought he had revealed. And in this case, no, it's not a tantric secret like in 15, but it will be significant the time that he spent in Italy collecting manuscripts that I think is informing this. Okay. Also, when I gave you a link to that article by Wilson, I basically gave you the solution, but I know it is a little bit difficult reading articles, even popular articles about mathematical solutions, and especially since Wilson's using a different translation because we hadn't done ours yet. By the way, Wilson and Alan Moore and I were, at the time that that came out, we were all living in the same place, Mount Gilead, North Carolina, which was also the home of Vincent Bridges and his partner, then the artist Darlene, who's written a wonderful article on looking at letters in the Enochian alphabets as waveforms. So it was a really fascinating time, but Dr. Turner and I were only up to Theorem 17. And Wilson was already looking at 20 going, oh, this is a coda for the ideas of conic sections. So, well, I'm excited about this theorem because this is a theorem where I think D is going to stumble onto the concept of 4 dimensions, something I won't talk about until the next video. That doesn't seem that that's why D is excited. In fact, one might argue that he's excited because he has solved the Delian problem. So we're going to see if, in fact, he has. Now, to understand what is happening here, I agree with Wilson's analysis that you want to look at this theorem as a kind of coda or a kind of conclusion for these ideas about conic sections as related to the Delian problem. You're going to have to suspend disbelief a little bit here, or at either that or just trust me or just trust Wilson, because the actual numbers you need to make this work, you don't get to theorem 23, but in 23 you do get the correct numbers. So that part of it works out. There are some other parts that I'm going to leave to you to figure out. And I'll talk about that more as we get further into this. All right. So we're going to also look at some of the theorems where he stressed ideas that are really important to solving the Delian problem. Among them, the first couple of theorems, Theorem 8, 10, 12, 13, 16. We're not going to look at all of those, but I'm going to refer to them. And I think you'll remember the things I'm talking about when I get to them. In the next video, when we talk about this in terms of a second solution for the doubling of the cube, we're going to need to look at what he means by center. And when we get to that one, we'll review 3, 6, and 7 again. But now, remember back to the very beginning, when we just started into the theorems, Theorem 1, D said, by virtue of the straight line and the circle, the first and most simple manifestation of all things, non-existent or merely hidden in the veils of nature, is produced in light. We talked about that most in terms of the need of light to be there. Fiat lux, or let there be light of Genesis 1, 3, and so on. But we also talked about how the straight line and circle are the things you need as a straight edge there and a compass to make compass and straight edge projections, which is just a given if you're doing ancient Greek geometry the ancient Greek way. The idea is you have a compass and straight edge construction, and in this case, it will be for the doubling of the cube. Modern mathematicians have since proved this is impossible, but you probably remember when I was talking about the squaring of the circle, That one reason modern mathematicians say it's impossible is they can calculate things way, way out. So with the doubling of the circle, you have pi. Pi is an irrational number, 3.1416 on out to infinity. So it's not a Euclidean number. Anything you do is going to be approximation. You have to have a fractional equivalent in that case. In this case, for the doubling of the cube problem, what you're going to need is a cubed root of 2, which is also an irrational number that you can just calculate way out and not a Euclidean number. But if you are tolerant of a bit of slop in there, maybe it will work if you just kind of want an approximate. We'll see if that happens. Anyway, in the second theorem, D alludes to this idea of compass and straight edge again when he says, neither the circle without the line nor the line without the point can be skillfully produced. Therefore, pierced by way of the monad, things are first begun, and that which is related to the periphery can in no way be employed without it. Lots of things happen. We get to Theorem 8. Theorem 8 seems to be how to make geometric constructions of letters. And the letter he is most excited about is the one that's 3 times 7, 21st letter of the Latin alphabet in D's time, not today, X, which is also the Greek chi. And there's various religious plays we can make with that because chi rho are the first 2 letters in Christos, the meaning the anointed one or Jesus. But we also, when we talked about that, had after Theorem 6 and 7, which you have no doubt reviewed, looked at again at D's habit of flipping things into 3 dimensions. Now, like, so every time you see a circle, you may wonder, is he flipping this into a sphere? Circle is a perfect form, and so is a sphere, and we talked about that as connected to things in Plato's Timaeus, right? So with the rectilinear cross, which is going to be very important again in 20, D said all of those things in 6 and 7 about, well, if you displace a point, you get the ternary and quaternary and so on. Also, if you flip these right angles, because it's rectilinear, recta can also mean a right angle in Latin. So you have this rectilinear cross, but if you flip it out, you get a square. Well, flip that to 3D and you get a cube. So how do we, is what we should do with this X, flip it into a cube? Well, sometimes we do that, but you can also flip it into this particular structure that you see here, which is 2 cones that are sharing a point, and they have the same axis of symmetry, this one here, labeled T, and that is perpendicular to this plane that is going through the vertex, which would be a Euclidean plane of reference if I can shift more to the way D would talk about it from the way that we talk about it, say, in algebra. Okay, let's jump forward to Theorem 16 and a few reminders about 16 that we need for our argument now. The main thing going on here in his wonderful, light of the cross as the crux of the matter is that he seems to be doing translations of these Roman numerals, L, which is 50, V, 5, denary, that would be 10, X. So he's signing in his text itself, LVX, Latin for light. He does it forward or following at least the direction of writing in Latin. Then he does it in reverse, following the direction of writing in Hebrew. And just in case you miss it, he does it a couple more times. He also says some other things just about the letter L. When he writes it out phonetically as L, that seems a reference to, Aleph Lamed, God Most High in Hebrew. And it is. And the denarian virtue of the cross is in a certain sense the 10 Sephiroth. But we're going to look at it in terms of conic sections, not anything else right now, because that's what we need for this theorem 20. Okay, so where do you get an L if this is the cross? Okay, remember there's the cross, X. Well, L would be, if you go down halfway down the axis of symmetry and out on the Euclidean plane, there it is. And by the rules of how you can flip and translate and rotate figures that are similar to one another, This could be the L2 if I go up here and out this way. In other words, it can be upside down and backwards. It's still an L. In the same way that he gives us the V right side up, but also upside down. These basically, he's just doing geometric transformations of different letters. We also realize in that theorem, though he never explicitly talks about conic sections, that if we realize that back in 8, that X was these, to borrow some language from Dan Winter, these kissing cones, then we can, if we move this Euclidean plane of reference around, we can get up to 7 different things, 7 being another important number to D. And in Plato's Timaeus, it's important, and in the Sefer Yetzirah, it's important, and so on. So if we do that, we can get a circle, an ellipse, a parabola, a hyperbola, a point, a line, and a cross. Yes, these all were known in Dee's day and in ancient Greece for that matter. It seems in 16 that he's mainly interested in these 3 where my cursor is circling, the point, line, and cross. That's, after all, what he's talking most about, is the light of the cross. But he does slip in a reference to a parabola, because L is also the notation for the lattice rectum of a parabola, which I'll talk about in another slide or two. That concept existed in Dee's day. It existed in ancient Greece. It comes in and is translated into Latin, and you get the variable L assigned to the lattice rectum. It's a chord that's going to be parallel to the directrix. We'll see it in a minute here. So here are these 4 conic sections. We're not concerned about the point, line, and cross for the moment. A circle, an ellipse, a parabola, and a hyperbola. This is just public domain graphics from Wikipedia. So if you need a review of the parabola, they've got a great one there. If you were to graph this out the way you might have done, well, in the US educational system, I think you'd probably do it in Algebra 2. That's when I remember in the dim long ago doing this. So the way you would express this is, here's the axis of symmetry. It's perpendicular to the directrix. You need a focus, this point here, and a directrix to define and graph a parabola. And the vertex is, of course, where this parabola is going to intersect the axis of symmetry. Now, this grid is a Cartesian grid. Of course, Dee didn't have a Cartesian grid, but the rest of these concepts he had, and they had them, for that matter, in Greece. If you had the habit, which most people do not, of thinking about parabolas all the time, and you looked at the hieroglyphic monad glyph, you might even look at it and think, wow, that describes a parabola. If we let this horizontal line here be the directrix, and we put this little center thing here of what's often the sun symbol right on the focus, then this parabola could be described by the hieroglyphic monad. Now, I know you have to be way into parabolas to do that, but if you look at people describing parabolas on YouTube, which frankly I've done a fair amount of, since I'm making these videos, I was like, wow, that looks like the hieroglyphic monad. It's not too far of a leap, and it is something also Wilson describes. I mean, you could even see this top thing here as parabola-like, when in fact it's a semicircle. It's not a parabola. Okay, so I want to take a moment and just talk about some of the fascinating properties of parabolas, and I'm doing this for a reason. This will link to the realpolitik that I wanted to bring up with this particular theorem. But there are fascinating reflecting and mirroring properties. So if you were directing light and you're out of the focus, one of the things that will happen is that it'll form beams that are collinear to the axis of symmetry, so you can get a really bright spotlight. But if the light is coming in the other way, suppose you're catching it with a parabolic mirror, you may have heard stories about the ancient Greeks coming up with these mirrors that were so powerful that they could catch the sun's rays and direct them out and hit a ship's sail and make the sail burst into flames. Okay, if one did that sort of thing, it's because of the fascinating properties of parabolic mirrors. That is, any light that comes in above the latus rectum here is going to reflect and hit the focus. It's also something that is basic to how a camera lens works. You have a focal length right here. It's the same thing as a focal length in cameras. Dee, remember, is an expert in optics. As I'm going to talk about in a moment, optics have great military uses along with great uses in photography. Incidentally, any other type of wave that you were using here, like a sound wave, also, there are interesting things that you can do with sound waves using parabolas. There are all kinds of uses. In fact, before there was anything like a modern calculator, and if someone wanted to add something up, there are ways that if you graph a parabola, you can use it as a kind of calculator. You can also use it as a different kind of compass. Da Vinci had a parabolic compass. You can use it to determine the center of gravity. Like if for some reason I want to balance my cell phone on my finger, well, I could use a parabola to figure out where I should put my finger so I can balance it. Now, Galileo, a name you no doubt recognize, a generation after Dee, proved that projectiles follow the course of a parabola. So you shoot something off and it has a parabolic path. Now, you can intuit that that might be true, and it is very possible that people knew that generations before Galileo and didn't express it in writing, because that combined with optics makes for some very interesting military secrets. Now, a little digression on realpolitik in the time that Dee is living in. He is much, he has a support of Queen Elizabeth, which is a great help to him. And Elizabeth comes to the throne after Queen Mary. Queen Mary had been married to Philip of Spain, if you remember that history. And so all of England became Catholic. And then she was called Bloody Mary because a lot of people who were Protestants were executed. And then she dies and Elizabeth comes to the throne, and Elizabeth turns England back into a Protestant country. And for all of Elizabeth's reign, which includes the time the Hieroglyphic Monad is written, there is the possibility of war with Spain. That comes to fruition in 1588 with the Spanish Armada, which England is not supposed to win. There are many explanations for why, ranging from witches in Scotland to John Dee and Edward Kelly kicking up an Enochian storm in Prague. But let's just look at mathematical and military, and also bad weather, which pushed the Spanish ships back, or paying off people in Amsterdam. I mean, there's all kinds of explanations. Some hold more water than others. Let's look at one involving optics and projectiles. Okay. One reason it's very difficult to know who created the first telescope is because having the optics to do that would be a state military secret or the equivalent of that. The way that you figure it out most easily is with applied algebra, which we don't know that Dee ever used, though he may well have known it since his stepson Digges used it, and his friend Thomas Harriot was the best person of his time, probably in terms of practical applications of that. But it's not written down how to do this, either how to algebraically explain things like parabolas or hyperbolas, or to apply it in the field of optics. So Dee has always been interested in optics, and if one person knows the theory, it's going to be Dee. In fact, to show you what a Dee scholar who is much better well known than I am, Deb Harkness, and also a fantastic fiction writer, what she does with that in her fiction is, in her All Souls trilogy, which involves some time travel lines and so on, she creates this fictional scenario where Harriet does discover that and gets credit for it hundreds of years later. I won't give away the whole plot twist, but the point is, there are reasons why these things weren't written down that have to do with optics, and which are mathematically most easily described with algebra, that have to do with defense, basically. Also, Two more examples before I move on. There is quite a history of hiding things that would be militarily useful in alchemical text, right? Because if this is supposed to be a text of physical alchemy, well, we know you can't really turn lead into gold, so we'll just ignore this. Well, you can hide things in it. So Roger Bacon, for example, a few centuries before Dee, and Roger Bacon, as you may know, Dee was one of his biggest Renaissance fans. Roger Bacon is describing the Philosopher's Stone in one of his writings, except an industrial engineer in the early part of the last century went through and read it and said, no, he's describing gunpowder. And sure enough, what Bacon is describing as the Philosopher's Stone was in fact gunpowder. Now, who knows what, if anything, is hidden in George Ripley's Compound of Alchemy. Remember, he's another physical alchemist that was a great favorite of Dee's. But when you get the first English translation of Ripley's Compound of Alchemy, you get a bunch of prefatory material, which includes a poem by Edward Kelly, a poem to Dee, and a long preface by a guy named Rafe Roberts. The only thing we know about Rafe Roberts, really, other than he was the person who wrote this introduction, is that apparently he's the first person we know who figured out how to mine harbors. So if the ship hits the mine, it'll explode, or at least it'll sink because it gets a hole in its hull. So alchemical texts are not always what you think, and they are a good place to hide knowledge. I am mentioning that because the Monas Hieroglyphica, in terms of the knowledge of conic sections, may well be one of those texts, and we will return to that after we continue talking a bit more about parabolas. Okay, here's those four conic sections again. Here's how you would graph them out today. All right, here's a circle. This is an ellipse. The blue one is a parabola. The green one, a hyperbola. You have things here labeled as E. That's the eccentricity. It wasn't called that as far as I know in Dee's time, but the concept existed. So if you have, this time it's tilted 90 degrees, so our axis of symmetry is here. It's X. And here's the origin. If you solve this algebraically to get the eccentricity, you get a non-negative real number that creates the shape. A non-negative real number is also what Dee would consider a Euclidean number. Now, figuring things out multiple decimal points is something they can't do, but dealing with eccentricities that equal 0 or 1, yeah, that's real easy to do. And note, it's important in the monad when something equals 1, because monad, monas, is unit, sometimes 1. In fact, that's how the term monas from Euclid's Elements is often translated, including by the person who did the first English translation. All right, so conic sections with the same eccentricity are said to be similar with one another. So a circle is always similar to another circle. That is, they share the same mathematical properties. They are just either the same shape, larger or smaller, or they've been flipped in a particular way or moved around on a plane. And I'll review the different types of transformations you can do that make things similar in a minute here. Parabolas are all similar. In effect, they're all the same parabola. I've dropped in a link to a video on that below. Regular polygons that have the same number of sides are similar. So equilateral triangles are similar to other equilateral triangles, but isosceles triangles, for example, aren't similar to other isosceles triangles necessarily. Squares are similar to squares, pentagons to pentagons, pentagrams to pentagrams, hexagrams to hexagrams. Now, these are also some shapes, at least in terms of triangles, squares, and hexagrams, that you might easily flip into 3D. You can't do it with a pentagon or pentagram. Also, things that are similar have lots of other properties that I'm not going to talk about. But if you flip some similar polygons into 3D, of course they're going to have different volumes, and the volumes aren't in a kind of linear proportion to one another. So the chance of having non-Euclidean numbers is very high, which is the problem that you get, as we will see, with the doubling the volume of the cube. But Any two parabolas are essentially the same parabola. They might look different, but that similarity is what gives it so many fascinating properties. So what you see on the screen here, it looks like one is a little wider than the other. They're the same parabola. If you tilted it this way, it would be the same parabola. If you moved it around on that line, I mean, mathematically, you can prove that it's the same thing. Okay. As we've gone through the monad and we flipped things within the same dimension, like in 16, or well, we've done it many places. We're in effect doing geometric translations or transformations, and that is probably why in 12 and 13, which remember Wilson talks about in that article, in 12 and 13, you get the glyphs for Saturn and Jupiter redrawn so that they're mirroring each other, and then in 13 they show up mirrored and on the same side of the thing they're rotating around. That's because, again, parabolas are, I think it is because, I can't prove this, but parabolas have fascinating mirroring properties. He says other reasons, which we've talked about, but the best known use to a layperson of a parabola is as something that has fascinating properties of mirroring and reflecting light. All right, so if we take L and we decide to do some geometric transformations with it, here's a black L. This blue L is the same L. This one here that is flipped upside down is the same L. They are all mathematically similar. What that means is one of four things. Either you're just moving it around to a different place on the plane, or you're rotating it a little bit, or it's a reflection or mirroring of it, or you're scaling it, you're making it larger or smaller, but they're all still similar. Now that brings us back to Wilson's article after all of that on parabolas, because I want to make sure that you understand the value of parabolas and all the things you can do with them, militarily and otherwise. All right, so if you haven't looked at that article, I'll drop in the link below. But one thing that, as I've mentioned, D doesn't give us the correct proportion to the values to construct it. That comes in 23, but they'll match up. Now, Wilson in this article says that Wilson is using the Jostyn translation, and the analysis is based purely at a mathematical level with only the inclusion of naive biblical prophecy and meaning. It thus invites an exploration of the more abstract metaphysical connotations. Okay, metaphysical connotations, abstract or not, I love them. That's the whole next video. But for now, I want to just go over some of the things Wilson says. Wilson establishes D's longstanding interest in the problem as expressed in the Propoitomata Aphoristica and later in the Intro to Elements. Now, J.L. Heilbron, who is a very respected history of science person who wrote the introduction to the only translation that exists of the Propoitomata Aphoristica, points out how interested D is in the doubling of the cube. And D, Heilbron says, and I agree, D kind of implies he solved the problem. Or to be more exact about that, he implies he has solved it the ancient Greek way with compass and straight edge. D has solved the problem. But does he solve it with a compass and straight edge? Heilbron would say no, and say that D is kind of equivocating. I want to see if there is a reason why D would be equivocating. D also implies this in his introduction to the first English translation, as I've mentioned. Now remember, just the year before, 1563, D is down there visiting the Duke of Milan, and the court mathematician is a very talented man named Federico Comandino. Comandino gives D a gift, De Superficierum Divisionibus Liber, which is on the division of figures, something that would seem to have influenced the monad also. And by 1570, these two have published it together. We know Comandino more today as somebody who went around looking for text, kind of like D, right? And republishing ancient Greek or Greek through Arabic treatises like this one, which actually it existed in Arabic, and he put it into Latin, and then he fixed up the Latin and then published it. Okay, so they share that interest, but why would Dee be welcome at the Duke of Urbino's residence anyway? Not because of his interests in Kabbalah, very likely, probably because of his interest in optics and because he's a very well-respected mathematician, even though it's apparent that many people couldn't understand what he was saying from some accounts you get of the math lectures he gave in Paris. But the Duke is the commander of the Papal army. The Papal army is fighting with the Ottoman Turks. So what are some things that they need? Well, the mathematics to create some good optics, some ways to figure out where projectiles might fall or how to aim them, because it's not like if you fire a gun and you look through a scope, you can basically figure your bullet's going to go in a straight line. I mean, it's not, but it's going fast enough. It seems that way. If you're firing things like cannonballs, you're firing them up and they're going to come down in a parabolic course. So with optics, you would need to know what that course, to be able to estimate what that is like, and with optics aim above so that you know where you're hitting. So in other words, the very thing that Dee is most noted for in science, optics, is something that you're really going to, the Duke of Urbino is really going to want to know. Dee also has done a lot of work with mapping. Remember, the Propoitomata Aphoristica originally was something he sent to Gerard Mercator of the famous Mercator Maps projection. So that could be another reason. But I'm bringing all this up because what I want to suggest for you is that, and Wilson doesn't say this, but I'm saying this, is that Dee is in effect giving you two solutions to this problem. One that works and one that is metaphysical, that people would maybe also get some religious value out of, but think wasn't, you know, of anything but religious interest, which today we would look at and say, hey, wait, he's defining a hypercube. Okay, now some quick background on the Delian problem, and then we'll finally get back to the text of this theorem. All right, here's the ruins of the Temple of Apollo at Delphi. The altar, according to legend, was a perfect cube. So there's the altar right there. Apparently, it was once a perfect cube. All right, that is the god Apollo, or a more modern sculpture of Apollo. So the story behind the Delian problem is this. Apollo sends a plague to the island of Delos. So the citizens go to see the oracle at Delphi and ask what do they need to do to solve, to stop this plague, because they're dying. In another account, the citizens are just fighting and they go and ask what do they need to do to stop the fighting. But in any case, the oracle at Delphi says they must double the volume of the cubical altar to Apollo. So they do what many people might do who don't know math or don't know volume very well, or they double the edges. Now that's a problem. It doesn't work. And you may know why it doesn't work. If you double the volume, all right, take an edge is 1, all right, to get the area of a square that has edges 1, you go 1 times 1, which is 1. Now you do it again to get the volume of a cube, 1 times 1 times 1, which is 1. But if you do that with 2, 2 times 2 times 2, you get 8. 8 isn't doubling it, right? It's a lot more. Now, for some reason, this upsets Apollo. I guess Apollo doesn't want more volume. Actually, Plato will tell us why Apollo was upset, but we're not there yet. You can find online lots of places, people talking about this, and particularly why the citizens mess up and they, instead of doubling the cube's volume, they make it 8 times larger. It's just, it sort of makes false common sense to do so. And it doesn't work, but you can kind of see how easily the error happens. So that didn't work. Now Apollo's upset. So they decide, all right, we know how we'll double the volume. We'll just stack one cube on top of another. The problem with that is then it's not a cube. It's two cubes stacked on top of each other. It's not one cube. So a little side comment, kind of tongue in cheek until I get to the next video. This might look like the double cubical altar some of you in esoteric orders use. And I know there are explanations for why you use it, like 10 faces that maybe correspond to the Sephiroth and so on. But gee, it would be kind of sad, wouldn't it, if part of the reason that for black cubical altars was making the same error as the citizens of Delos did? Hopefully there's some other reason that you have this doubling of the cube represented this way, because that's not the doubling of the cube. That's not a cube. And there will be, but we won't get to it till the next video. All right, so the citizens go to see Plato, of course, and according to Eratosthenes in a famous work called the Platonicus, Plato says, you know, the whole reason Apollo is upset and the whole reason this problem happened to begin with is you citizens neglected your math. Shame on you. And you have contempt for geometry. So that's not a good thing. So then Plato calls in some of the best minds. He gives the problem to several people, including Hippocrates of Chios. That's not the same Hippocrates as the one associated with medicine, by the way. It's a different Hippocrates who writes a book called Elements, which is the first Elements, and it's before Euclid's Elements, which comes like 100 years later. And then another person called Menachmus. And Menachmus is the person who likely discovered conic sections. And he solves this using intersecting parabolas. In fact, as the story goes, he discovered the whole concept of what a parabola was because of this doubling of the volume of the cube problem. Now, he didn't solve it algebraically, which is how we'll do it now. No one really knows how he figured it out, just that his solution was right. One speculation is he did it with pins and strings. There's a video, I've dropped a link in below, of a guy that using a rope is showing how you could figure this out. And you use two double cubes, by the way, if you're figuring it out like that. You could also put marks on a straight edge and get an approximation. But the thing is, you're not supposed to use anything but a compass and a straight edge, and an unmarked straight edge. Now, why that is, that's another whole discussion. But what's important for you to know here is that this problem was solved. It's been solved since ancient times. It's been solved since before Euclid's Elements. It just wasn't solved with a compass and straight edge. And the way that D, if you look at the shapes rather than the words, and you sort of morph the words to mean one thing for this solution and another thing in his other solution, D's other solution seems a little suspect, but he solves it correctly with two intersecting parabolas if you have already had something, have some knowledge of what parabolas are. So the general problem that you're trying to solve here, you could express as finding the volume of a cube whose ratio to another given cube's volume is the ratio of two given lines. Why is that? Because you got to build the cube. And so you measure the edge of the first cube. You don't know what the edge of the second one is going to be, but you know how to get the volume of the first cube. And so you're trying to double that. So you have that variable also for the second one. The way that this gets worked out is with something called mean proportionals. I'm going to drop in another link below from someone at St. Andrew's College who works out all the math for you. So I'm going to talk about the concepts, but you can do the math on this and it works out. I'll give you a little of that, but not all of it. So the idea with mean proportionals is that between two cubic numbers, there are two mean proportional numbers, and the cube has to be the cube, the ratio. It's the ratio cube of that which the side has to the other side. I'm sorry, I have a little bit of a typo in there and stumbled. But this is just in Euclid's Elements. And remember, Euclid's is after Menachmus, and this is in book 8 if you want to look it up. And we also talked last video about how D is using the idea of hypostasis. usually a religious term, which is used to explain how Jesus can be perfectly divine and perfectly human, but it is adopted by an Alexandrian writer in the 1st century to be a mathematical concept of numbers that have the same substance. I mention that because cubic numbers as a class of numbers are not hypostatic with each other, which could help what he's saying a little bit, except they're not hypostatic. All right, now to figure out the volume using mean proportionals, you can either follow the math with the link I've dropped below, or I will tell you a little bit more about it. You'd have, if you do this, you can reduce it different ways and shift it around. So you get a quadratic equation, and one of the most simple quadratic equations, and that is what you're going to graph. And if you graph it, you get 2 parabolas. If you set the length of the first cube's edge to 1, actually you can set it to anything, you just get a more complicated equation. Today, mathematicians, like I said, have proved that you can't do this with a compass and straight edge. It is mainly because of this cubed root of 2, which is an irrational number. But since Plato's time, or Monochmus's time, the solution to this problem has existed. You solve it with parabolas. You can't solve it with compass and straight edge. Plato didn't like that. In fact, Plato goes on a whole rant about how this is a mechanical solution and that's bad and you shouldn't do it. In fact, Dee uses in other contexts the same language of a mechanical, that is a machine that you make to create something. He uses that in his intro to Euclid. You even see that term used in Shakespeare's Midsummer Night's Dream, when some of the characters who are doing things talk about mechanicals. Okay, so just to give you a quick idea of what we're talking about and what is in that longer article. So if you know that the edge of the cube you're working with is 1, and you know that the volume of this cube is 1, it's 1 cubed, which is 1, then you can set up an algebraic equation. So you know doubling the volume just means 2 times this cubed root. Now, if you solve this all out algebraically, that's where you get the cubed root of 2. All right. If math doesn't thrill you, we're done with math, but not quite with parabolas. We're back to Wilson's argument. And remember that Wilson put it together by looking at the shapes that Dee has been using, not the text. He doesn't get to the text till the very end of that article. And by knowing Dee's background in optics and the similar references in the Propoidomata, like I've mentioned, and the intro to the first English translation of Euclid. At the very end, Wilson will get to the text, where Wilson analyzes parts of the text as referring to the duplication process. That's, on one hand, that's the mathematics you would need to do to solve the doubling of the cube problem with parabolas. And at the same time, it is the novel or transcendental solution, which we're going to discuss in the next video. But before I wrap this up, I want to show you a couple more things, and the first is the places I'm talking about in Wilson's article. So you should be seeing Wilson's article now, and in this whole opening part, Wilson is talking about the history of the mathematical history of this problem. Then you get down to this graphic, same one I've been showing you, where Wilson suggests that this is looking at the intersection of the cube, and we're using this as a directrix and so on. And then when you get to the very end of it, using the Jostyn translation, what you get are the ways that Wilson interprets this to connect to the Delian problem. Okay, so let me go back to my slides here. And if I just imported what Wilson is doing there into the translation that Dr. Turner and I did, we could go through this first paragraph, which I went through in the last video, and see how to interpret that. We've sufficiently demonstrated above using in good faith hieroglyphical calculations and so on that the elements are signified by straight lines. That again is just right out of Euclid. And then we are going to explore the most central point of our cross. We're in the solution that mathematicians would agree works. You make that the focus, but that's also the light of the cross. Oh, light and parabolas. When I finally realized what was going on there, my arms got all tingly. That's maybe too much information, okay? And as concerns our ternary, there's multiple meanings, okay? Wilson gives you some interpretations, but there are multiple meanings, and you keep going. And then when you get to the binary, there are multiple meanings. An obvious one, not mentioned by Wilson, but that I want to tell you before next time is as above, so below. I mean, this is demonstrating those Hermetic maxims. Another, since we're going to talk about hypostasis, is the idea of Jesus as associated with the Christos, as associated with Tifereth, which would be associated with that middle point on the monad, as divine or Tiferetic, and man, cross of the elements, as associated with, as we heard in a very early theorem, with earth. So you're going to be moving up and down on the middle pillar for the metaphysical explanation that mathematicians, particularly in Dee's day, would have no time for, but that might have some religious significance. Okay, and I will continue on with looking at this in terms of both solutions with an emphasis on the hypercube solution next time. Oops, those came up out of order, but we'll just leave it. So if we think about what D is realizing there, what if that's a blind, or at best a riddle? Because what it seems like D is being so secretive about is conic sections. He never mentions, for example, the cone back in Theorem 8, not in Theorem 16, but he seems to be building upon the same thing. And if there were any doubt at all, we know that he has been interested in this problem of the doubling of the cube since, back before he wrote the Hieroglyphic Monad in the Propoitomata, and probably before that. And his interest continues after that. So one reason he'd be so secretive is because of the useful military implications, both in terms of optics, in terms of firing projectiles like cannonballs. And yes, here he is writing to Maximilian, who soon will become the Holy Roman Emperor. And before, when he was visiting Comendino, he's visiting the Duke who is in charge of the papal armies. So you have to think, well, do they understand what he's talking about? My personal thought is that Maximilian probably didn't carry and other people figure out that kind of stuff for him, but could be wrong. And the other thing is, in the time that D is writing this, there was a very intense diplomatic flirtation, so to speak, going on between England and Spain, because there was the real politic also of Elizabeth I not having an heir, which continued all through her reign. And so there were some people, among them William Cecil, who were playing both sides, England and Spain, until, and another was Robert Dudley, who many people suspect was her boyfriend early on. They're playing both sides of England and Spain because they're worried about war, among other things, also single women who have power, I would say. But there are reasons that Dee would be secretive about these things. And the person that we know he explained the monad to was Elizabeth I. Also then, when C.H. Jostyn, back in the last scholarly translation in 1964, writes his introduction, he says that the meaning of the hieroglyphic monad is now lost, which I don't agree with, or I wouldn't be doing these videos. But he said that apparently there was this sort of side oral teaching given to a group of mystiae or initiates, and that is what is lost. What I would submit is there were probably two different groups of initiates. The one that we would think of today as initiates, people who are into magic, Kabbalah, and esoteric work, Christian Kabbalah, so Christian magical initiates, But there's also a group of initiates that are science initiates that want to know how to do things like successfully fire projectiles, make telescopes, and that D is their or one of their theoretic sources for people like Harriet, for example, doing those. Now, ironically, the conic section problems that were such a secret then and allow you to do those things aren't even difficult math now. They're like algebra 2 math. I mean, I'm no mathematician, and if I can understand them, they're not difficult math. They don't require any cover story today. They just require that you go to high school and understand algebra. But in yet another twist, by needing to create what I take as a cover story for the things he's communicating about conic sections here, he's going to find his transcendental fourth dimensional solution. And that, my friends, is what we will talk about next time. Have a great day. Bye-bye.